We often think of the big AI models as these impenetrable digital fortresses, billion-dollar black boxes. But what if I told you there's a way to pick the lock and steal some of the crown jewels for less than 20 bucks? We're diving into a paper today that does exactly that, showing how a clever attack can expose the secret architecture of major production models.
And let's be clear, this secrecy is completely by design. The companies building these models are incredibly tight-lipped. I mean, just look at this quote from the GPT-4 technical report. They basically tell us nothing. The goal is to make them completely opaque from the outside.
So that really brings us to the core question this paper asks. How secure is that black box really? What can an attacker actually figure out just by using the public API, the same way you or I would?
Well, it turns out the answer is a lot. The researchers behind this work proved that the fortress is not nearly as secure as we thought. For less than $20, they were able to run an attack that successfully extracted a key piece of the model's architecture, its hidden dimension, from production models like OpenAI's Ada and Babbage.
So here's how we're going to break down this incredible heist. First, we'll talk about why this black box secrecy exists. Then, the Achilles heel that makes the whole thing possible. We'll walk through the attack blueprint, see how it was adapted for the real world, look at the stunning results, and finally, discuss the security arms race this research has kicked off.
Okay, let's start there. Host B, why do these companies guard their model architectures so fiercely?
Well, Host A, it really boils down to two things: a massive competitive advantage and, of course, security. If you know the exact architecture, it becomes way easier to design other attacks, like trying to get the model to reveal training data. This whole field is often called model stealing. What's so new and important about this paper, though, is that it moves beyond just copying a model's behavior. This is about stealing the actual, precise, high-fidelity parameters from a live production transformer.
Right, so these are incredibly complex systems. But for an attack like this to work, there has to be some kind of fundamental vulnerability. What's the crack in the armor here?
The Achilles heel, as it turns out, is in the model's final step. It's called the embedding projection layer. So after the model does all its complex internal processing, what you could call its thought or its hidden state, this is the layer that has to translate that internal concept into scores for every single possible word or token it could output.
And this is where the genius of the paper's insight really shines. It's all about a huge mismatch in size. The model's internal thought space, that's the hidden dimension, H, is maybe a few thousand dimensions deep. But the vocabulary, L, is enormous, often over 100,000 tokens. So you're projecting from a small space into a giant one. The authors use a great analogy. It's like a 3D object casting a 2D shadow. No matter how complex that object is, its shadow is always confined to 2 dimensions. It's the same here. All the possible output vectors are trapped in this smaller H-dimensional subspace, and that is the weakness.
Okay, so the model's outputs are fundamentally constrained. How did the researchers turn that insight into an attack? Let's start with the perfect scenario, the idealized heist, where they have full access to everything.
In a perfect world, the plan is beautifully simple. You just query the model a bunch of times with random inputs. For each one, you collect the full output logit vector, the scores for all 100,000 plus tokens. You stack all these vectors into a big matrix. And then you unleash a powerful linear algebra tool called singular value decomposition, or SVD. Essentially, SVD is designed to find the most important dimensions in a set of data. So when you run it on this matrix of outputs, it tells you the exact dimensionality of that subspace we talked about. And that number is H, the model's hidden dimension.
And it works just as cleanly in practice as it does in theory. Take a look at Figure 1 from the paper. They tested this on an open-source model where they already knew the hidden dimension was 2048. You can see as they collect more and more output vectors, the number of significant dimensions they find keeps climbing until it hits 2048. And then it just flatlines. It's a perfect plateau. They've measured the size of the shadow precisely.
And if there were any doubt, Figure 2 makes it crystal clear. This graph plots the gap between each singular value and the next. It's pretty much flat until you get to the 2048th value. And then, bam! You see this massive spike. That's the cliff edge where the real, meaningful dimensions end and the numerical noise begins. It's not an estimate. It's a direct measurement. That is incredibly clean. But of course, that's the idealized version. The real world is always messier. What's the big hurdle when you try to apply this to a real production API? You're right.
The main challenge is that no production API is going to send you that massive 100,000 dimension vector. It's just not practical. Instead, what you get back are the probabilities for maybe the top 5 most likely tokens. So the very data you need to run the SVD analysis is almost entirely hidden from view. You need a workaround, a very clever one.
And this is where the research gets really ingenious. They found a feature in many APIs called Logit bias, which lets a user artificially inflate the score of any token they want. So they developed a system. First, they'd make a normal query and pick a reference token from the top 5 results. Then they would systematically go through every other token in the vocabulary one by one and send a new query, this time adding a huge bias to force that new token into the top 5. By comparing the new token's probability to the reference tokens, they could calculate the exact difference in their original scores. They just do this over and over, piece by piece, until they've reconstructed the entire secret Logit vector.
That's an amazing piece of reverse engineering. So they found a way to get the data. What happened when they aimed this attack at actual live production models from OpenAI?
The results are frankly stunning. You can see them right here in this table from the paper. The attack worked flawlessly. For OpenAI's Auto model, they pulled out a hidden dimension of 1024. For Babbage, 2048. And as you can see in the third column, OpenAI actually confirmed these numbers were exactly right. Now look at the last column. The cost to unearth these closely guarded secrets was less than $2. It's practically free.
And it gets even better. That was just the cost to find the dimension size. The paper goes on to estimate that if you wanted to recover the entire projection matrix for a more modern model like GPT 3.5-Turbo Instruct, it would still cost less than $2,000. For a well-funded adversary, that's just pocket change. This is a huge deal. It moves model stealing from an academic curiosity to a very real, very practical threat. So what was the fallout from this? How did the industry react? And what does this mean for AI security going forward?
Well, after the researchers responsibly disclosed their findings, providers like OpenAI and Google moved pretty quickly to put up defenses. You can see some of them here. Some are simple mitigations, like just not letting you use Logit_bias and request probabilities at the same time. Others are more extreme, like removing the feature completely. But that's the classic security trade-off, right? Logit_bias has legitimate uses, so removing it hurts regular users. It's a real cat-and-mouse game.
And that's really the core takeaway here. This paper isn't just about one specific attack on one specific layer. It's an existence proof. It proves, without a doubt, that you can extract precise, important architectural information from these massive, closed-source models. It has officially shifted model stealing out of the realm of theory and into practical reality.
Which leaves us with the really big and maybe uncomfortable final question. This attack exploited one small API feature. How many other unintentional backdoors are just waiting to be discovered? As we build more and more of our world on top of these models, you have to wonder, is it truly secure black box LLM even possible?
Or is their fundamental mathematical nature always going to leave a crack in the door for someone clever enough to find it?